Welcome back. Lecture 39, Segment 1. Today, we're going to learn how to evaluate delta H reaction. So, in the previous lecture, we have derived this energy balance equation for a steady state operation. And today, we're going to learn how to evaluate the delta H reaction term. طيب, to begin with, what is the meaning of delta H reaction? Like, what's the physical meaning? And how is it mathematically defined? Well, the physical meaning of delta H reaction is delta H reaction is the amount of heat that need to be exchanged with the reaction mixture in order to proceed the reaction at constant temperature. So, if a given reaction, like the one shown here, was exothermic and delta H reaction was minus 100 kilojoule per mole. So that means if I want to run the reaction at a given temperature, tamam, let's assume that this delta H reaction was given for the temperature of 100 degrees C. So if I want to run this reaction at 100 degrees C without increasing the temperature, so I have to remove 100 kilojoule of heat for every 1 mole of a reactant. And how is it mathematically defined? Well, it's mathematically defined this way, which you are familiar with, right? Delta H reaction, summation of nu I HIT. So basically, you are saying the enthalpy of the product minus the enthalpy of the reactant, each multiplied by the stoichiometric coefficient. Okay, so for the given reaction here, you can write the delta H reaction at temperature T equals D over A HD at T plus C over A HC at T minus B over A times HB at T minus HA at T. Type. In general, you know that delta H equals the integration of Cp dt, correct? So what is delta H? So let's say H for a given species I at a given desired, or at a desired temperature, minus the reference H standard enthalpy for species I at a reference temperature equals the integration of Cpi for that species dt from Tr, this guy, to T. And if Cp was constant or can be taken as an average value, it can go outside the integration and you get Cp delta T. Tamam. Okay, so that means if I take this term to the other side here, we get Hi at any temperature. Can find from this equation standard Hi at T reference plus Cpi delta T. Of course, the standard here refers to the standard state, which refers to pure species I. So you have standard Hi, right? So we're referring to pure I. And at 1 bar, and at a specified state, whether it is gas, in this case, ideal gas should be, was a standard, or liquid or solid. طيب, so let's substitute this equation into this equation. So for every H, we will have now two terms. One is the standard H at a reference temperature, and the other one is the Cp delta T. So here we have 4 terms, 1, 2, 3, 4. We'll end up now with 8 terms. And let's lump them together. All the variables which are the same or similar, lump them together. Okay, so we'll end up with this equation. Here, this is the first part, which is all contains the H enthalpy, standard enthalpy, and this is the term which involves all the CPs. Of course, we are taking delta T as a common factor. طيب, so again, this is the equation. You know this term already. This is the standard delta H reaction at a reference temperature, right? Good. What about the other term? This guy. This is the delta Cp, the heat capacity change of reaction. So therefore, I can write this equation as standard. So basically, I'm saying delta H reaction at a given temperature equals the standard delta H reaction at a reference temperature plus delta Cp times T minus Tr. Okay, so this equation gives the heat of reaction at any temperature in terms of the standard heat of reaction. When we say standard heat of reaction, again, we mean 1 bar, right? And the species are pure and the states are defined. Okay, tamam. At a reference temperature. So that means the reference temperature is not part of the reference state, shabab, huh? So the reference temperature, this guy, is not part of the reference state. Okay, and the reference temperature usually used 298, and so that we can find the test reaction from these two terms, from this term and the delta Cp term. Okay, so let's again look at what we are doing here. Okay, we want delta H reaction at a certain condition of the reaction. Hello? Where are we gonna start from? Well, we say delta H reaction at a given temperature equals the standard delta H reaction at a reference temperature plus the correction factors. How many correction factors we need to add? Well, we need to add 3 correction factors. One is related to temperature, correct? Because this is at TR, but this is at T. And one is related to pressure. We're not showing it here because this guy is at 1 bar, but this guy could be at other pressures. And the third correction factor has to do with the phase. Maybe this value was calculated for a reaction in the liquid phase. But when I go up to T, from TR when I go up to T, now all the reactants and products are in the gas phase. So I need to add a correction for the phase as well. Tamam? Okay, nevertheless, techniques for determining delta H reaction at pressure above 1 bar can be found elsewhere. So we're not going to discuss it here. Tamam? However, for the reaction of hydrogen and nitrogen at 400 degrees C, it was shown that delta H reaction increased by only 6% as pressure was raised from 1 atmosphere to 200 atmosphere. So an increase of 200 times in pressure, 200 times, increased the delta H reaction by only 6%. So that means delta H reaction is not a strong function of pressure. Why is that? If you remember well, because enthalpy is not a strong function of pressure. In fact, the enthalpy of ideal gases are not function of pressure at all. It's only function of temperature. Okay, so another question. How this term here, the standard delta H reaction at the reference temperature is practically calculated. Where do we calculate it from? Do we calculate it from the mathematical definition of delta H reaction, which is summation of nu I hi standard at Tr. Well, no, we don't do this. Although this is the definition, but the problem with this equation that we do not have the absolute values of enthalpies. We do not have the absolute values of enthalpies. So if you see tabulated data for enthalpies at different temperatures for a given species, these are not the actual, these are not the absolute enthalpies. They are only in a reference to its enthalpy at another reference. Tamam? So we do not have the absolute enthalpies, therefore we cannot use them to subtract from the enthalpies of other species, which again we don't have their absolute values. So this will not give you a correct answer. So how do we get the delta H reaction then? You got it right, from the delta H formation. Exactly, from the standard delta H formation. Let's go back to thermo 1, for instance, for this reaction, which you know its name. It is the reverse water gas shift reaction. Remember this reaction, CO with H2O giving you CO2 plus hydrogen. This is the water gas shift reaction. So now we have the reverse water gas shift reaction. If you want to calculate the delta H reaction, standard delta H reaction for this reaction, then you will need to use the delta H formation for the involved species. So let's see, we start with the delta H formation for the product, of course, right? So we have for water, this is the delta H formation. For CO, this is the delta H formation. Tamam. And for CO2, of course, we take the opposite, right? We don't take the formation of CO2, we take the opposite of the formation. That's why the equation is written this way, and here you have minus delta H formation because it's a product. Tamam. And then for hydrogen, it's an element. Okay, so we are assuming arbitrary that all the elements have delta H formation of 0. So let's actually sum up the equations here. So let's sum up these equations. Tamam. And if you sum up these equations, you will get this equation given here. Is that true? Yes, it is, because the C will cancel with C, and then you have here the oxygen cancels out with these two oxygen, so the remaining is H2, water, CO, and CO2. So as you can see, we did not use the last equation. That's why we don't need it. That's why we say arbitrary the delta H formation for elements are 0, because actually we don't use it. Tamam? Okay, and then of course the same way we sum the stoichiometric equations, we have to sum all the delta H formation. We'll sum them together, we get this value. So now this is the delta H reaction evaluated from delta H formation. Okay, calculating the heat of reaction. Calculate the heat of reaction for the synthesis of ammonia from hydrogen and nitrogen at 150 degrees C in kilocalorie per mole of nitrogen reacted, and also in kilocalorie per mole of hydrogen reacted. Additional information are given. You have the CPs of all the gases, the average CPs, ammonia, nitrogen, hydrogen. And the CP of liquid ammonia, liquid nitrogen is given as well. Sorry, liquid ammonia. Liquid ammonia is given. CP is liquid ammonia. And the delta H vaporization for ammonia is given as well at its normal boiling point. At its normal boiling point. That means this is the temperature which boils at 1 atmosphere. What else is given? Delta H formation for ammonia is given minus 11,020 calorie per mole. Okay, so we need delta H reaction at 150 degrees C. The first thing to do is write the stoichiometric equation. So we need it for per mole of nitrogen reacted. So we write the stoichiometry on basis of per mole of nitrogen. N2 equals plus 3 hydrogen gives you 2 ammonia molecules, or 2 moles of ammonia, 2 NH3. Okay, next write the equation. So this is the equation. Delta H reaction at any temperature equals the standard delta H reaction at a reference temperature plus delta Cp times T minus Tr. So what do we need to evaluate? Well, we need to evaluate this guy, and we need to evaluate the delta Cp. And then T is 150 degrees C. T reference is 25 degree C. تمام? Okay, because I have the delta H formation 25. So how do you calculate the standard delta H reaction at 25 degree C? Well, you calculate it from the delta H formation. So all what you need is 2 times, so you have the delta H reaction at 25 degrees C equals, what does it equal? Was 2 times delta H formation for ammonia at 25 degree C, correct? تمام, minus delta H formation for nitrogen, of course, at 25 degrees C, minus 3 times delta H formation for hydrogen, also at 25 degree C. But of course, this is 0, this is 0, and we have 2 times delta H formation for ammonia at 25. We'll give you the delta H reaction, standard delta H reaction for this reaction as written. Right, what about delta Cp? Well, you know that delta Cp equals 2 Cp of ammonia, right, minus 3 Cp of hydrogen minus Cp of nitrogen. Okay, but the question is, which CPs we're gonna use, and do we need to use delta H vaporization here or not in all of these calculations? Well, let's go to the CPs. Tamam. So the reaction is going from 25 degrees C, correct, to 150 degrees C. So the reaction was first calculated at 25 degrees C, right? And then we are using that to calculate the delta H reaction at 150 degrees C. So when I'm going through the calculation, not practically, not actually, through the calculation from 25 degrees C to 150 degrees C, do I have phase change? Well, let's see. Of course, at 25 degrees C, you know that hydrogen and nitrogen both are gas, but let's say ammonia. Well, ammonia evaporates at minus 33.4 degrees C. So that means at 25 degrees C, it's gas. So all the species are in the gas phase at 25 degrees C, and they are all also in the gas phase at 150 degrees C. So I discard any delta H vaporization, I discard any CPs for the liquid. Tamam? So I use all the CPs for the gases. Okay, so let's write the solution then. Okay, so delta H reaction at 150 degrees C equals okay, equals just erase these guys. Okay, what does it equal? Well, it equals standard delta H reaction at a reference temperature, which we just calculated, which is basically 2 times this value, plus delta Cp, which we calculated also from the Cp of gases as we showed, and then this 125 is basically 150 minus 25 degree, and we get minus 22,000 minus 1,000. Okay, the reason, Shabab, I wrote these two numbers because I want to show you that the majority of the value is coming from the delta H, and only a small portion is coming from the correction. Only small portion coming from the correction. Tamam? Why is that? Because usually delta Cp is small and the delta T are small as well. Tamam? Therefore, the correction factor is small compared to the reference amount. Okay. So when you sum up these two guys, you get this answer. Just make sure, Shabab, that usually when you are calculating, make sure that the units of the delta H reaction, standard delta reaction as reference temperature, is the same as the units of delta Cp, so that you don't do any mistakes. Okay, so the answer is minus 23.3 kilocalorie per mole of nitrogen. If you want to find it for hydrogen, you don't need to repeat all the calculation. All what you use is the stoichiometry and the conversion factor. Let's look at the energy balance again. This is written in terms of enthalpies. We can write it in terms of CPs. So this delta H can be written as CPI TI minus TI feed. Okay, because that's the feed. And this guy can also be written in terms of CPs as standard delta reaction TR plus delta Cp T minus TR. So basically this is the energy balance in terms of mean or constant heat capacities. In most systems, work is neglected. So this is really neglected. Why? Well, maybe we don't have shaft work, or maybe the shaft work is very small compared to the other terms, like in CSTR, for instance. But if it was a gas turbine, I could, of course, cannot really neglect the shaft work. Also, in most systems, all reactants enter at the same temperature, T0. So is the case for the leaving products, T. So all the reactants or all the feed comes at the same temperature, T0, and all the product feed leave at the same temperature. So there is no need to put an I here for every species. So we just write it without the I, and then we also remove the shaft work if it was not significant. So this equation can be used to relate T to X and then proceed with the CRE algorithm. Remember, Shabab, the whole rationale of us being in this chapter is that we needed an equation for T. So we can use this equation to find an equation for T as a function of X. And then we can continue with our CRE algorithm and solve the unknowns and design the reactor. However, unless the reaction is carried out adiabatically, this equation is still difficult to manipulate to find T as a function of X. Why is that? Well, basically because we have T here, and it will be difficult to solve for T. Because in non-adiabatic reactors, the heat exchange with the system varies along the length of the reactor. So let's recall that Q dot can be calculated either from UA delta T log mean, and in this case we have here T here and T here, or it's the integration of UA TA minus TdV. So whatever, whether you use this or we use this and substitute it here, it will be very difficult to solve for t as a function of x and other things. Okay, so it's pretty problem. We have a problem here. This problem does not occur in adiabatic reactors, which are frequently found in industry. However, if this guy was 0, now it is very easy to solve this equation in terms of t, or solve it for t in terms of x. Therefore, the adiabatic reactor will be analyzed first. See you in a bit.